Hey there, and welcome back to our STL mastery journey. Today is day 4, and we are diving into a really important and practical part of the C++ standard template library, vector modifiers and capacity. We will often find ourselves using vectors for dynamic data, and knowing how to modify them efficiently can make our code cleaner, faster, and much easier to maintain. We will also uncover how vectors handle memory allocation behind the scenes, an essential piece for writing high performance applications. Let's take a look at what we are aiming to learn today. We will start with vector modifier functions like insert, erase, and emplace back, which allow us to manipulate the contents of our vector in powerful ways. Next, we will talk about memory management, including how vectors grow, what capacity means, and how to reverse or shrink memory proactively. Finally, we will explore best practices and common pitfalls, especially around iterator invalidation. And of course, we will end with real world code examples and hands on activities to reinforce our understanding. C++ vectors can come equipped with a rich set of modifier functions. These aren't just bells and whistles, they are essential tools you will use daily. Functions like pushback and popback add or remove elements from the end of the vector. Dot insert lets us place element at any position, while erase helps us remove specific entries. Then there's clear for whipping the entire container and resize for adjusting the number of elements. And finally, the modern C++ starts emplace and emplace back, which create objects directly in place, avoiding unnecessary copying or moving. Each of these has specific use cases, performance implications, and behaviors that we'll break down today. Let's walk through a concrete example to see these modifiers in action. We start with a simple vector of integers 1, 2, 3. We use pushback 4 to add an element to the end, making it 1, 2, 3, 4. Then popback removes the last element. We are back to 1, 2, 3. Next, insert v.begin, 0 places a 0 at the beginning, while erase v.begin plus 1 removes the second element. Finally, clear whips the entire vector. Notice how intuitive this sequence is. Each line changes the vector in a clear and controlled way, but underneath there are performance and memory considerations we will soon explore. Now let's talk about a more efficient alternative to pushback, emplace back. Imagine you are using a custom type like a point start with x and y values. When you use pushback point 1, 2, a temporary object is created, then moved or copied into the vector. But with emplace back 1, 2, the object is constructed directly in the memory of the vector. No temporary object, no extra copy. This subtle difference becomes a big win in performance critical code, especially in loops or large datasets. Always prefer emplace back when dealing with user defined types. Let's shift gears to something less visible but equally important, vector capacity. The size of a vector tells us how many elements it currently holds, but capacity tells us how much memory it has reserved. This matters because vectors grow dynamically, and when they run out of space, they allocate new memory and copy all the elements over, which is expensive. Using reverse and lets us pre-allocate memory, avoiding those costly reallocations. Shrink to fit does the opposite. It tries to reduce unused memory after shrinking the size. Understanding and managing capacity helps us write smoother, faster programs, especially in data-heavy context. This slide shows a common behavior, exponential growth in capacity. When we push elements into a vector in a loop, it does not grow one by one. Instead, it often doubles its capacity to avoid frequent reallocations. In this example, every time we call pushback, we print the size and capacity. You will notice that the capacity jumps even if size increases linearly. This is a deliberate design choice for performance, but it also means you might allocate more memory than needed, hence the value of rewards and shrink to fit. Here's a common point of confusion: resize versus rewards. Let's clarify. Rewards 100 allocates memory for 100 elements, but does not add them. The size stays the same, 0 if it was empty. On the other hand, resize 100 actually inserts 100 default initialized elements into the array or the vector. If you are prepping a vector for incoming data, use rewards. But if you need the elements in place, maybe for initialization or fixed length buffers, go for resize. Now it's time to put your knowledge to the test. Write a function that does three things. First, insert -1 before every odd number. Then remove all even numbers from the vector. Finally, resize the vector to only 5 elements. This exercise will help reinforce your understanding of how insert, erase, and resize interact, and how every operation affects both size and capacity. Here's another challenge. Test the performance of emplaceback against pushback using a custom class like person. Use the chrono library to measure time taken during insertion. This will give us first-hand experience of how emplace really shines when dealing with constructors and object creation. It's one thing to know it in theory. Now you will see the numbers yourself. Let's recap what we have learned. You can now use vector modifiers like insert, erase, and emplaceback confidently. You understand how vector capacity works and how to optimize it with reverse and resize. You know when to use emplace over push and how to manage vector growth for performance. And perhaps most importantly, you are now aware of the subtle costs and pitfalls of careless vector manipulation. To reinforce today's lesson, here are a few practical exercises. First, build a basic book catalog system that uses pushback, insert, and erase to manage books. Second, simulate an undo feature using popback. And finally, for deeper learning, simulate a dynamic array using raw pointers and compare the complexity with STL vectors. This will help you appreciate why STL exists and how much heavy lifting it does behind the scenes. And that's a wrap for our day 4. Today we moved beyond just using vectors and learned how to control them like pros, modifying their content, managing memory, and optimizing behavior. Remember, mastery of modifiers and capacity management makes our code not only more elegant but far more efficient. Feel free to ask questions, share your thoughts, or jump straight into the activities. I will see you in the next session.